Thank you, everybody. Thank you for joining the session on next generation AI processor and why we need them and why we need to think it differently with Eric Duffy. My name is Faraz, and I'm one of the co-organizers here at ML Ops World. Just before we begin, if you have any questions, please feel free to ask them in the chat with a Q in front so that we can collect and we can address them in the end. Please also visit our partners in the booth section on the left-hand side to hear more from them, but also to enter in some very exciting giveaways. Tenstorrent is actually our gold sponsor, so please do visit them in the booth. So it's my absolute pleasure to welcome Eric again. Eric is the Business Development Director at Tenstorrent, a company designing microprocessors tailored for machine learning training and inference workload from the edge to data center. Eric's experience in the AI domain spans 15 years, having developed computer vision applications for life sciences, consulted on AI with the United Nations Technology Division, and having worked at a large FinTech on next generation services. So welcome, Eric, and over to you.
Thanks so much, Faraz. And we've got a pretty small crowd in the room today. So what I'm going to do is just encourage people just to ask questions that are going. I am keeping one eye on the chat window there. So I don't think you have the option to jump in necessarily, but do feel free to post any questions. So yeah, thanks very much all for joining. I am sitting in Toronto this morning after a very heavy night of thunder and lightning. I don't know how everybody else on the Northeast is doing, but we've been getting some big rain here. But in the meantime, I will also apologize because I have a 3.5-month-old sitting upstairs and she might be a little noisy. So if there's any issues hearing me, do just ping me in the chat and I will address that pretty quickly. But just to get started, format for today, I've done a number of presentations with TMLS in the past. But one of the previous presentations was talking about the death of Moore's law, essentially, and is that something we need to consider as we go forward? Why it is, why it isn't. This takes a similar approach, thinking about the increase in compute demands over time versus the increase in compute supply. And this is one of the things that Tenstorrent's considering very closely. And it looks like we also have one of my colleagues, Kevin, in the room as well. Hi, thanks for joining, Kevin. Good, so kicking off, let me just spend a couple of minutes introducing the company because you won't all have heard of Tenstorrent before. We're not new necessarily. We've been around for about 5 years, but we are an AI startup. And as Faraz mentioned at the top of our meeting, we are working on what we consider next gen AI processing technology. So processors specifically designed to be very, very good at deep learning tasks. And really, we've been working under relative stealth mode for the last, let's say, for the first 3 or 4 years. We really only started to approach the market in the last year or so. But we have technology that actually, Faraz said, you know, we're an inferencing technology. We are actually designed to do both training and inferencing. Which is putting us in a great spot because there's certainly demands for both types of workloads in the marketplace. We've been growing quite substantially over the last little while. When I joined literally a year ago, almost to the day, and at that time we were only 60 people. Now we are up to well over 120 people. We've been increasing our engineering workforce quite substantially, and we were joined in January by the legendary chip designer Jim Keller. And if you haven't heard of Jim Keller before, I'd encourage you to Google his Lex Friedman interview because that is quite eye-opening. But he talks in quite a lot of depth about the way that processing technology has evolved over time and what his vision is for the future. And you know, he's been pretty on the money with regards to the incremental changes over time. So if this is an area that interests you and machine learning and the data sciences and processing fast is something that's an interesting thing to you, I would encourage you to check that out. Just Google or go onto YouTube and look up Jim Keller, Lex Friedman. Jim was also incidentally our very first investor. He gave us our first 100K back in the day. I call that the angel round or something along those lines. But as of May, we became another of Toronto's unicorn status companies. We raised an additional 157 million on top of our previous funding, and got a valuation of over $1 billion. So we're doing well, and this funding will take us through to IPO. Now, what we've been considering as we're going forward in designing our technology is, well, we want to design technology which is first and foremost very good at AI processing in particular. So this is a notion of, but within the deep learning space, there obviously are multiple types of models, right? So we want to be able to tackle all different types of deep learning workloads, whether they are computer vision workloads, whether they are natural language workloads, large transformers, and we've designed our stack to be very malleable in that way. We are architecturally quite similar to a GPU in some ways, in that our processors are designed for very high degrees of parallelism. So all of those operations that need to be done in line together can be done very effectively and very quickly. As I mentioned, we're working towards both training and inferencing workloads, and certainly one of the things we've seen in the marketplace, we're not the only AI chip company out there, but often, the companies will approach the market with a very specific proprietary ML framework. We thought it would be most appropriate to go to market with a technology that is usable by the community, essentially, and the best way to get adoption and get real use out of this is to use frameworks that people already know. So we've designed our compilers to be PyTorch friendly, for instance, or be able to compile other languages as well. And we'll go through some of these things in detail. And certainly got a note here that says we're scalable from the edge to the data center, and that's certainly true. Our units, which I'll show you in a second, are relatively small, low in power, and small PCIe cards that can be linked together across multiple units and treated essentially as a single contiguous compute workload, compute unit. And that can go from one card all the way up to really an arbitrary number of cards, more particularly in the next generation, which I'll give you a sneak preview of towards the end. Let's look at the problem we're seeing first. So we've seen this, I would imagine most of you have heard this concept of software 2.0, and this is something that Andrej Karpathy, the lead the lead AI scientist at Tesla, had commented on. And interestingly, actually, Andrej was brought on by Jim at Tesla. At the time, they were using NVIDIA technology, and there were challenges in coding down to the low level on the NVIDIA technology. They had to essentially define a net new compiler for their processor. And so Andrej came in at the request of Jim and built up that compiler to support the development of new low-level operations on the NVIDIA stack. They ended up actually building their own in-house processor after that, but that was the start of Andrej's career at Tesla. So he's been talking about this shift from handwritten code, as you see on the left, to relatively undefined code, not written by a person, but written essentially through the training process, and it becomes very nebulous very quickly, trying to decode this neural net. A lot of people look at neural networks as black boxes. Andrej has noted here that he tried actually writing a neural net by hand, and he does say it's quite tricky. So I think that's something we're going to see a shift towards over time, and I think I'm probably preaching to the choir there when I say that. This is something that's happening quite quickly. We're seeing a big adoption of transformer technology over the last couple of years in particular. Before I go too much further, I thought it'd be quite cool just to have a preview of what these boards are actually looking like. Now, these are now in our shop. We've had, much like other chip companies out there, we've been hit by supply chain challenges over the last year, and literally this month we're starting to get our boards in that we're going to be selling as of next month, which is quite exciting, at least for me. We have a couple of different flavors that we're bringing in. So we have this small board, which is about this size, and I know that's kind of hard to get a perspective of over camera, but it's a little larger, let's say, than a pixel or something like this, maybe this size. And then we have these larger boards, and so those run at 75 watts, which is relatively low power, and you can imagine that being applied in an edge situation. Then we have these larger boards which can fit up to 2 of our processors on them. And what you're seeing there, that little silvery box, that is our Grayskull processor. And these larger boards, they can fit either 1 or 2 Grayskull processors on them. Each Grayskull processor has 8 gig of memory on board, or actually on chip. And I'll show you what that looks like. And what we're finding is we are able to build workstations that can have up to 4 boards inside them. And 4 boards could be the dual capacity boards. They're the dual chip boards for pretty high density workstations, and up to 8 boards inside a 2U enclosure like this. So you can have up to 16 chips. And these boxes here, if you have 16 chips inside them, are roughly equivalent in throughput to, let's say, an NVIDIA DGX system. So one of NVIDIA's top of the line AI processing boxes. This is a bit of a cartoon diagram. It's obviously not a real technical diagram, but it's a nice representation of what the Grayskull processor looks like underneath. So we have these 10 by 12 array of 10.6 cores. That's 10.6 there. And inside each of these 10.6 cores, we have 5 RISC-V cores. That's those there. We have this packet compute engine. We have a packet manager, and a meg and a bit of SRAM. I think it's 1.2 megabits, so about a floppy disk worth of SRAM there. Floppy disk. So we also have 8 gig of I'm just having a bit of an existential crisis there. Sorry about that. I'm just realizing my age. 8 gig of DDR4 sitting around the edge there as well. And all of the heavy math happens within this packet compute engine here. You might think, well, what's happening with those RISC-V cores then? Those are more to deal with what we call it's called a network on chip. So each of these 10.6 cores is connected directly to each of the adjacent 10.6 cores. And actually, each of the edge 10.6 cores wraps around and is connected to the opposing edge. And that's described as a 2D bidirectional torus. And what that does is it allows us to pipeline data across these chips very, very efficiently. Network on chip is not something that's standard in GPUs or anything along those lines. Very few organizations are approaching the architecture in that way, but we are, and it drives quite a lot of benefits by having this network on chip architecture. And I think that's something you're going to see quite a lot in the coming years. Now, this chip all sits on a PCIe Gen 4 bus, and that's standard, a standard bus for high-end processors these days. But what we're finding is in our own builds, finding compatible motherboards can be a bit of a challenge. And certainly the x86 processors that go alongside these, there's only a few that are compatible today, but we're going to see more and more of those chips becoming Gen 4 compatible over time, because it does allow for higher data flows between the processing units and obviously the back-end system. Anything else I want to talk about on this slide? I guess the point here is you can imagine building multiples of these Grayskull chips into 2U enclosures, and you can build up racks into rows of racks very, very quickly. Just a quick chat about the software, and I'm going to come back to this because I do have some interesting updates around the direction our software is heading. Now, I mentioned at the top of my conversation that one of the things we had been thinking about very carefully was this notion that, well, it's got to be usable, it's got to be accessible by the community. And so, as I mentioned, we have this direct PyTorch compilation path. So any PyTorch model that exists that you are running already will run on a Tenstorrent card. And we had a decision to make fundamentally, because writing compilers is no mean feat. It takes time. Obviously, these languages are changing and growing. In particular, open source languages are being adapted and improved all the time. So we're working hard to make that our software is up to date with the latest editions of PyTorch, so that all those functions that people use are available to them. And then we have this other compile path through Onyx, which is, if you ever used an Azure system, you'll have seen Onyx before. If you haven't used Azure and you use GCP or AWS for cloud compute, you may not be familiar with Onyx, but this is the Open Neural Network Exchange. This was an open project that was, it's kind of like an intermediate representation layer between these high-level representations and lower-level representations. And this works pretty well in an inference path. But the general idea here is we should be able to compile anything that comes in from any source language, and in all different types of formats, which is pretty cool. So let me talk now. So I'm giving you that high-level overview of the hardware and the software stack. Let's talk more about the problem we're seeing in the marketplace, because I think this harkens back to the comments I was talking about Moore's Law. And this is a slide I borrowed from that Moore's Law presentation, actually. So what we see here, this is an exponential graph on the left-hand side here, and this is time on the x-axis. So we have this gradient here is representative of the doubling of processor speeds every year. But what we're seeing over the last, let's say, what year is it now? 2021. We're seeing a different exponent on this side. A steeper gradient means a higher exponent. And so what this is essentially saying, this is if you imagine this line here being compute demand, and this line here being compute supply, there's a mismatch. And so we're going to get to the point where training larger models with larger sets of parameters is becoming cost prohibitive, time prohibitive. And in fact, I mean, GPT-3, which is probably still the state of the art in ML model technology today, would sit somewhere up here. It's a large model. One of our researching partners suggested that to train GPT-3 on a single A100 instance would take somewhere in the order of 350 years to train a multi-billion parameter model. So obviously for most organizations, that's not something that's going to be feasible. And if you were to spend $5 million, you would be able to bring that time down quite substantially and do it in the order of weeks or months. But again, a $5 million investment isn't the kind of thing that many small organizations or many even business units within larger organizations can afford to bite off. So we're thinking, well, how can we bring this down, drive down the costs of compute in general? And so this is the problem that we're tackling essentially. And we're tackling this certainly through aggressively increasing the processing capacity. Like that's essentially table stakes for organizations that are developing processors. But we also need to be smart about what we compute, right? And what we compute is often wasted cycles, right? But there's a lot of work that's done by these processors that essentially doesn't need to be done in order to drive accurate results. And one of the things that's becoming increasingly popular in the marketplace is this notion of taking advantage of sparsity in graphs. And for those who aren't familiar with this notion of sparsity, I like to just spend a couple of minutes talking about this picture, this terrible picture of a dog I drew. And I'll apologize for it, but let's call him Snowy for now, little white dog. So in a computer vision model or in a computer vision task, right, you would have a layer mask going across this model. And actually, I did animate this, so let's just go full screen here for a second. And you can imagine a layer mask going across the model, apply multiple layer masks, looking for features within the data. And at the end, it will match those features to a labeled data set, and the classification will come out indicating that, okay, this was a dog. But as you saw, there was a lot of zeros in my binary dog here. And I should have said, this is supposed to be a representation of that same picture. I did just push this through a little processor to make that picture. So if you squint really hard, you might be able to see the outline there of that dog. But my point here being, there is a ton of zeros in here, which don't add anything to the end result. So imagine instead we could remove those zeros and only focus on the areas where things actually matter. So this is my sparsified dog. And what I like to talk about is this notion that matrix in matrix multiplications, which is essentially the underlying work that's being done, you take your activations, you take your weights, you multiply those two matrices against each other, and you get a matrix of results. And that would, fully dense matrices will grow exponentially over time, will drive up computation time exponentially over time as the number of parameters increases. And matrix multiplication is an extremely expensive task, right? And I like to run this little video because I thought this was cool. This was something I found on Reddit, and it seems pretty stuttery on my side. But the notion here is, we know in school that any factor that you add in here multiplied by 0 is going to lead to a zero-sum result. Computers, they don't have that intuition natively, right? And so the idea here is, if you could just eliminate factors where one of the matmuls, and if you can reduce the instances where it's 0 or close to 0 as one of the factors, then that's going to drive a significant speed ups. And so this is a different spin on this picture. We did a number of experiments on sparsity in particular, trying different sparsification methods. And interestingly, what we've discovered is you can fairly randomly select nodes for pruning in your matrices and still end up with very, very good results. Now, I should say, we don't take a fully randomized approach in sparsifying our matrices, but this is something that we are doing dynamically at runtime. We can actually induce sparsity into the models, and using a masking technique and a subsampling technique. Essentially, what we're doing is we're going over groups of these nodes within the matrices as a pre-processing technique, and subsampling down. So you can imagine some nodes might be a light shade of pink or empty. If they're a light shade of pink and empty and no high significance nodes, we could just have the most significant node be focused on. And by sparsifying the weights and the activations, we can go from this ON cubed complexity, so exponential complexity, as each of these axes are defined by the number of parameters you're adding. So you can imagine, as these axes go out, both the activations and the weights axes will increase, and so the multiplication of this times this plus this times this plus this times this will also increase. Now, if you strip that down, you can get actually down to almost linear complexity. And so what this does, well, like, okay, Eric, so you can strip all this down, you can heavily sparsify these matrices. What effect does that have for me? It opens the doors to much larger training on much larger data sets. And so what we're having interesting conversations with companies now about is, multi-billion parameter models running on extremely large clusters of these grayscale processors. Because the nice thing is, not only is it driving down the volume compute, but it's also driving down things like the memory requirements as well for training and inferencing on these processes. So that's sparsity, but it's not the only thing we're doing. There's other conditional execution techniques that we're integrating into our product as well. So one of the cool things is, well, if you have a set level of confidence that you know in advance that you only need the model to be 80% confident in its prediction, then why continue computing up to the 95, 96% confidence level? And so we have the ability to interject between the process and say, well, if it gets to that level of confidence, stop processing. Great. We also have this ability to add conditionals in graphs. So we could start building things like decision trees. If it's, you have multiple graphs chained together, and you can imagine having subgraphs within there as well. So this is the concept of dynamic routing. And what this does is it gives us the opportunity to drive very high throughput on our processors, and to the point where we're competing with the market leaders in this space. So this would be, well, let's imagine this is an NVIDIA A100 chip, because it is. And this is running around about, well, depending on the power you run it at, somewhere between 300 and 400 watts. Ours is actually 75 watts, but just for the sake of comparison, it's easier to see that this is a quarter of the power, let's say, of those A100 devices. The cost of those devices is much higher than ours. Ours is about, let's say, about a tenth of the cost. But our throughput is generally similar, if not better, than on those chips. And so we're getting this performance per dollar advantage. And if you're not familiar with the chip space, that's a fairly common metric in this space of about 10x, about an order of magnitude better on a performance per dollar basis. And we're running all different types of models, as I mentioned. BERT's running really well on our system. We actually had a big company offsite a couple of weeks ago. One of my colleagues had spun up BERT as a kind of a Jeopardy game, as an in-house demo, and that's working really well. ResNet 50 is running for computer vision applications. We've ran some recommender systems as well. DLRM is working. The only thing about DLRM is it is quite memory intensive, so we did actually add some additional memory on board as well. So that's, to be totally fair, I did adjust this number because this number would be much higher on a performance per dollar basis, up to like 49x if we didn't make that adjustment. So this is, I did mention at the top of the conversation, and I just realized here I can't see the chat anymore, so I'm just going to go back to presenter mode. Oh, I'm seeing a question from Ronnie here. What about quantum computing to optimize training times? Ronnie, do you mind expanding on your question? So is the question, will quantum computing help drive faster training times over time? I think my sense is, there's a couple of interesting companies working on ML in quantum systems right now, but it's, as you rightly called out, it's a fledgling technology, and it's perhaps too early to tell what the impact of quantum processing is going to be. Our focus is really on more traditional silicon at this stage. But it's an interesting thought. The number of qubits in these processors has been increasing quite dramatically over the last 3 or 4 years, and I think we will see some changes. But my ability to comment on what impact it will have on training times, I do imagine it will shrink them. But the degree to that is to be determined. I think you'll still see the need for smart programmatic techniques one way or the other, because quantum processing is an expensive technology, and frankly, taking this kind of traditionalist brute force approach of processing everything is not going to be feasible going forward. That's my read. So I imagine you'll have some of these techniques that I'm describing in my presentation here, some of these the conditional compute techniques combined with quantum technology. And yeah, I think this notion of dynamic sparsity in particular is what really sold me on Tenstorrent in the first place. As I mentioned, I joined a year ago when the company was still quite unheard of, and my background as a computer scientist, this notion of driving down operational complexity from exponential to linear is like it was quite eye-opening. And my question was, well, if this is possible, well, why isn't everybody doing this? Like, why wouldn't we incorporate sparsity into all GPU design, for instance? And the answer is fundamentally, it's hard to do, right? You have to do it at a very low level of the stack, and companies that are established, like NVIDIA, aren't really necessarily keyed up in the right way to be able to do that. It takes a real investment at a low level to design the processors to be very, very good at these matrix multiplication operations, and very good at the sparsification operations as well. And so there's a bit of secret sauce under the hood that's made us quite good at that stuff. So I do imagine you'll see similar techniques being used in other companies going down the path. It just so happens that we happen to be ahead of the game there, which is good for us. But I think companies like Tenstorrent will drive a demand for these types of techniques going forward as well. So I told you earlier I did want to come back to the software slide, and there's been a couple of interesting things that have happened within the software layer since I last presented the TMLS. So first off, we made an announcement in a recent podcast with Ian Cuttress and Anantech that we'd be going fully open source with our stack. So this entire, everything from obviously the PyTorch component is open source already, but all of our compiler, all of our parallelizer, all of our kernel will be opened up fully so that people can experiment, can define their own very low level operations, which interestingly the market is demanding. There's a lot of, particularly in the ML engineering community, there's a lot of like raw hacker types who are very interested in being able to try different things and define their own custom operations. And more so in the scientific community as well. There are new operations that our customers are interested in defining themselves. Those with advanced math degrees have new ideas they would like to try out, and so being able to access that low level is going to be very useful. And as far as I'm aware, we are the only company to make the commitment to go fully open source with our stack, and so that will be distributed via GitHub. You'll be able to download it, poke around, see what we're doing, see how we're implementing sparsity. And so and perhaps the obvious next question as well, is that going to kill your competitive differentiation? I don't think so, really. I think that one way or the other companies are going to see these techniques and are going to build their own approaches in a similar way. There's no way to stem the tide too long against that. We have other competitive differentiators. We are competing heavily on cost. One of the things I didn't mention on the hardware side is we're integrating commodity components. We played around with trying HBM, for instance, and seeing if that would improve our fetch request for data. The short answer is it didn't. It didn't make any difference to our processing times whatsoever. And using commodity DRAM actually worked really, really well, and it drives down the cost quite substantially of these boards. But we're also using larger node sizes than some of our competition as well, and we're still getting similar throughput. It's another way we're able to drive down the costs. So I was talking about this. I talked about going fully open source. Buddha is a new layer that's going to sit between PyTorch and the compiler, which will be essentially a C++ API that will allow for some really fine-grained graph manipulation as well. So you've got this high-level abstract representation in PyTorch, which will compile into a Buddha, essentially a Buddha model, which is written in C. C obviously with some PyTorch hooks, but you will be able to see exactly the different nodes on each of the different operations in the graph, and we're combining that with some interesting utilities that our software engineering team only really came out with literally a couple of weeks ago, that will allow you to see individual operations and their placement on the chip. So you can actually define where on the chip those individual operations will go and start drawing out a pipeline of operations across the chip. And what that will do is it will show, issues like bottlenecks in certain operations, so you can think about how to unconstrain those bottlenecks. It will allow for some really interesting tweaking and manipulation of those graphs to drive some really, really impressive efficiencies. So our hope really is that companies will do it. I think I'm probably going to wrap it up pretty quickly because I might be talking too long here.
You are slightly over, but that's okay.
Okay, well, I'll just wrap it up pretty quickly then, because I got a bit chatty. Here's some of the models that we've tested on our boards. So BERT's running really well, Transformer's running really well. We have a number of image of vision models here as well, so ResNet's running well. Transformers, we're seeing more and more vision transformers crop up apart from language transformers, so that's kind of cool. I want to spend just a second looking at the roadmap here as well. So the next generation of our chip is going to have 16 ports of Ethernet sitting around the edge and an integrated switch. And so what it's going to let us do is have chip-to-chip communication in the data center for essentially an arbitrary number of chips all working together as a single compute unit, which is going to be really cool, and that's going to drive some really interesting changes. We got a customer already who's placed an order for 500 of these to build a really large cluster. And the next generation, we're going to be actually integrating some custom RISC-V CPU cores. So this will essentially be like, if you imagine like a Raspberry Pi for ML, this will be a device which will be completely independent, whereas these would be hooked up with an x86 host. This will be a completely independent unit that could, you can imagine it sitting on the side of a 5G tower or something like that for real-time data inference. You can imagine all kinds of different scenarios for this. And then, of course, we're going to be shrinking the density. These are just kind of table stakes, or shrinking the node size to increase density. Got to do that. But I think we're going to see some interesting changes in the coming weeks. In the coming years. So last thing, quick pitch. If you are an organization that's doing data science, doing machine learning, and you are in a pretty advanced state, and what I've described today is kind of interesting to you, do feel free to send me a note. I'll stick my email address in the chat, but also what you can do is you can just go to the Tenstorrent website, and I'm just going to shrink this down. Sorry, Faraz, give me 2 seconds. I'm going to wrap up in less than a minute.
No worries at all.
Once I finish my quick pitch here, you can go into contact us, fill it in, and that will come straight to me. So please do reach out. Be very happy to talk about applications where we could work together. And that's it. Thanks all.
Awesome. Thank you so much, Eric. It's always very fascinating to hear kind of the direction and kind of the future of chips as well too. So it's great. We do have a question as a follow-up question from Ronnie. She was asking kind of who is your intended client base, and also like how do you envision competing with like AWS or Google or kind of like other cloud providers on the cloud side?
Yeah, I realized I didn't answer that question now. Yeah, so the intended client base at this stage is we're really focusing on AI experts. So small startups, organizations that have large compute needs, but are perhaps cost sensitive, because we are quite a bit more cost competitive than other companies. We're looking to engage with people who are used to dealing with nascent technologies, who are comfortable in programming with low-level frameworks, who are willing to work with an organization in a kind of a partnership mode, because as we're still building up, the software stack competency, it would be nice to get feedback and develop a bit of a relationship with the community. As time goes on and our software stack and our hardware becomes more robust and market friendly, we'll be going out to larger organizations and selling these to enterprise scales and that kind of a thing. Not to say that we're not interested in engaging with enterprises, but typically we find that you can go down a bit of a rabbit hole with some enterprises that are perhaps a bit more dispersed, right? So long term, we're going to be pushing into enterprises and hyperscalers. And the question with regards to how will we compete with AWS, Google, and other cloud providers? Well, we are working on a cloud service to allow for cloud compute directly through Tenstorrent. But also, as this programming paradigm and as the hardware becomes more prolific in the marketplace, we anticipate that you'll see Tenstorrent products being listed as options within AWS and GCP as well. So I think there will be a bit of competition, a bit of co-opetition, as they call it. So hopefully that answers Ronnie's question. I see she's not here anymore, but
that's great.
Insightful for Narendra.
Mm-hmm. Oh yeah, yes. I think the uniqueness is the hardware and the software, right? So like I think like that's the uniqueness that comes from Tenstorrent, and having that succinct ecosystem and the talking between the hardware and the software. I think it's going to be a fantastic kind of coexistence between them, for sure. Yeah.
I think so, and the hope is, the community will respond to this, and already we're getting lots of very interested parties. So, if anybody here would like to be part of that, let me know.
Absolutely. And then you had mentioned kind of the cards will be released shortly. So like where can someone know? Is that through the contact form, or where can someone know kind of when the cards are being released?
Yeah, great question. So if somebody has interest in purchasing a Tenstorrent card, right now we're being quite managed with the way we would put them into the marketplace. We will be opening up an e-commerce channel in the not too distant future, so people can buy low volumes directly. But in the short term, talk to me, and I'll be happy to put you on our list.
Oh, that's great. Yeah. And then maybe just very briefly, can you expand on kind of the difference between kind of the small, medium, and the fast? You had gone through that in the slide. Maybe if you can just yeah.
Yeah. So the small board, it's kind of like it's the E75 is what we call it. So it's a low power 75-watt board with a single Grayskull processor on it. The medium board has a single Grayskull processor on it, but it operates a little bit of higher power. So if you look at the website, you would see, the increasing the power on these chips will give you a little bit of extra throughput on them. And then obviously the fast board is a dual chip board with 300 watts of power draw, and that's let's call it our highest density solution that would be targeted more towards data center applications. But that's something that we've been experimenting with as well in our lab, and we're finding that those will fit into even workstations as well. You just have to have the right enclosure. You have to have the right motherboard, and we can help you through that as well. We actually will be selling these as systems with fully loaded with Grayskull boards. So it's basically, you just want to buy a system off a rack, we'll do that. We'll help you out with it.
Absolutely. Yeah. That's definitely going to help a lot of practitioners kind of just order it on the e-commerce side and kind of get the opportunity to play with it.
Yeah, I think it will be fun as we start to see this in the hands of the community. We've started a Discord channel as well, where we'll start inviting people to swap notes on how they've had good experiences on their cards, ask questions of us as well, because my colleagues will be manning the Discord channel as well, and there will be a bit of moderation there. So if people have problems, if people have issues, bring it to us through that chat, and everybody can see. We're going to, transparency and openness is one of our core tenets. We want to be totally open with regards to, how things are going, and when changes will come and when improvements will be made. We won't be hiding anything under the covers. We'll be pretty transparent with everything.
That's great. Perfect. Awesome. Thank you so much, Eric, for your time, for a very fascinating presentation, and thanks everyone for joining.